Okay, it's high time to start. Hello, my name is Athanас Бъчваров, and I am System and Signal Processing Engineer at certain company. Anyway, it's not important. And we are going to talk about booting free Berkeley Unix under Microsoft DOS operating system, or the equivalent of Microsoft DOS, PC DOS, whatever DOS. But the main idea is that we are going to use DOS as a standard environment which we are going to use. So, reasons, of course, reasons. Why in the world would anybody want to boot Berkeley Unix under DOS? And of course, the first reason would be embedded systems or appliances. It's quite reasonable because MS-DOS provides us with quite a few things which we are going to discuss later in this talk. So, embedded appliances, we said, how about support? It's very easy to upgrade something which is running MS-DOS or PC-DOS or whatever DOS. And of course, easier support is a point. And of course, easy upgrade is also a point, because you can just copy some files here and there, and you end up with bootable system, which is going to just boot and start your appliance with Berkeley Unix operating system. And how are we going to boot Berkeley Unix from MS-DOS? So, the usual way Berkeley Unix boots is reading the master boot record on the PCs, and it loads it and starts the code there. It's a tiny amount of code. We are talking about a few hundred bytes of assembly language code, which is insufficient, but just right to load the next stage. And the next stage is Boot-wane. Boot-wane is not so complex piece of code, but good enough to be able to load boot2, the next sequence. And boot2 is actually a complex piece of assembly language. Boot2 is capable of loading the next boot stage. And boot2 is actually using complex assembly, like in entering protected mode, leaving protected mode, etc., etc. Of course, boot2 is supposed to load some arguments to the kernel, like in which is the booting device, where we are booting from. The kernel has to know them, all of them. And of course, the next stage is our /boot/loader. Loader code is something which we are going to discuss later. But it's the third stage of the loading process, and it's extremely complex. It knows a lot of things. And of course, it runs in protected mode, which means that you just cannot bypass it in any way. So, the first thing which happens is that the boot2 stage activates the BTX kernel. Loader is linked against a microkernel which provides several system calls. And it's called BTX. And the syscalls which it provides are called exec and exit. But, well, we are not talking about standard Unix syscalls. We are talking about something extremely specific. So BTX provides exec, and the arguments of exec are quite different from the arguments you expect, let's say, from the usual Unix exec syscall. It also provides exit, which is the panic way. If something goes wrong, the loader will just issue exit. And of course, it knows several file systems. And we are talking about CDFS, which is ISO 9660, as well as MS-DOS-FS, as well as extended second file system, few others as well. It's upgradable. The latest versions of FreeBSD also support ZFS. You can read the whole thing here. Well, you'll see quite a few things there anyway. So, it also knows several different devices like HDD, hard drive, or CD. And the loading process actually points the bootloader towards the right boot device. And it boots from there. It's good enough. And of course, the /boot/loader also links against the so-called libstand. And libstand provides us with standalone functions and features, quite a few actually. Libstand supports MS-DOS file system, FAT, as well as extended second, the Linux file system, as well as CDFS, like ISO, blah, 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 etc. And libstand is a K library inside the loader. Without libstand, the loader itself won't be able to read any file system at all. All the functionality is exported to libstand. And of course, our very nice loader also has a Fort interpreter. Just like the standard OK prompt you see on every Sun computer, anyway, either server or workstation. The Fort prompt is, let's say, quite powerful. You can change the very way your kernel is booting. And we have it as well. It's just like Sun OBP, the Open Boot. And unlike the other Berkeley operating systems like NetBSD or OpenBSD, FreeBSD has a very complex, I would rather say extremely complex boot procedure, because the loader itself decides which parts of the kernel, like ACPI, etc., will be loaded. And because of this, we need something which is quite complex. So, our very nice /boot/loader is quite intelligent and it decides few things fast. It just, let's say, loads the appropriate modules fast. So it's intelligent anyway. And of course, depending on the very hardware you're using, it's going to load the appropriate modules with the very kernel. And of course, it can hint the kernel by providing it with enough information about devices and, well, ports, etc. It's called device hints. If you open this file, you'll see quite a few entries there which are directly exported to the kernel, and they define the appropriate ports and interrupts, etc. for every single device in your system. Well, it's not important anymore because we have modern PCs where everything is configured via SM bus or PCI itself. Anyway, nobody cares. And of course, our very good loader can also load modules for us, because there is another file which is called /boot/loader.conf, which provides the loader with the information it needs. You can define which module is going to load at boot time. Okay. So, we're talking about booting FreeBSD from MS-DOS. What is MS-DOS? We have a FAT file system, which is very good because FAT is, let's say, very easy file system. It's not very hard to use it or to read a file from it, anything. You can do whatever you want. And of course, it's a single process operating system, excluding the TSR, the terminate but stay resident procedures in MS-DOS. We are talking about a single process operating system, which is also quite good. And of course, it has no inherent memory management at all. You can, of course, load some memory management drivers like EMM386 or HIMEM.sys, wherever. But there are just some drivers you add. They add the so-called VHCI capabilities to MS-DOS. In theory, you don't need them. I mean, a pure DOS with pure BIOS is just right and just enough. If you know well enough about your CPU, you'll be able to do whatever you want with your memory, etc. And of course, MS-DOS runs in real mode every time, at all times. Which is not exactly true if you have EMM386.exe loaded in your memory from config.sys. If you have it, you end up with some virtual system like MS-DOS running in VM86 mode, but that's not important as well, because you still have the VCPI interface. Anyway, that's not important at all. And of course, it's single user. It's DOS. Come on. It does not know about any different user besides the one standing at the console or at the terminal. So, we want to boot the beastie. How are we going to do this? There are several different BSDs in existence, and all of them are quite different. I mean, you are not supposed to boot another BSD with the same loader. It's not going to work at all. FreeBSD, my favorite BSD, is actually changing quite fast. And by changing, I mean the very binary objects are different between different releases. So you won't be able to boot anything, let's say kernel, wherever. You won't be able to load a module with the upcoming next release. So if you write something for FreeBSD, let's say 7 or 8, you probably won't be able to boot anything from FreeBSD 9er. FreeBSD is changing a lot. It may work today, but what about the next release? What's going to happen with the next release? Your software is not going to work at all. It's not so nice, but who cares? We're talking about very, very system software. And what exactly is not changing between different releases? That's the point. That's the very point. And of course, our very nice loader is not changing at all. Bootloader /boot/loader is staying the same every time. It does not change. I mean, you can load it because it's still a.out object, and you can deal with it. Anyway, we will see that in the following slides. But, of course, it knows well enough how to boot the rest of the system. And we said that bootloader knows quite a few things about BSD, and it knows the /boot hierarchy, and it knows the modules, all of them, and it knows how to load the kernel, etc. So bootloader is our best friend in this endeavor. Yeah, I already said that. It's a.out binary. It's linked in a non-standard way. You have to link it against the BTX system, which is very, very, very simple kernel, which only provides several syscalls, like exec and exit. It was somewhere before this slide, but it was there. So, sure, I can return my presentation to that particular slide, which describes the syscalls BTX provides. It's very easy. It's just like few page ups. Who cares? Anyway, so loader is actually I should have brought my laser. Anyway, so boot/boot/loader is a client of BTX. It's a program which is, let's say, managed by BTX. BTX kernel is good enough to provide several syscalls, and the boot process is going to use them anyway. So, boot/boot/loader and MS-DOS. I already said that the /boot tree is to be present on your FAT file system. You just cannot overcome this. this is extremely important that you have it. And, of course, bootloader is few hundred kilobytes. In real mode, on a PC, you only have about 640 kilobytes. Unfortunately, that's true. Like the Spark systems, where you have whatever memory you have installed on them. Yeah. And you can access all of it anyway. Because the CPUs boot in supervisor mode, which means that you have access to everything. Like the PCs, unfortunately, we are limited by some architecture built by IBM about, let's say, 30 years ago or something. It's complete bullshit. And I wonder why they are still trying to be compatible with it. It's unnecessary. Yeah. Do you remember who said that 640 kilobytes is enough? Well, it's not enough. The /boot/loader program is about 250 kilobytes. Now what? We have to load it. So, it's very easy. We have to load it. There is a.out header /boot/loader is a.out binary, which means that it's very easy to process it. And if we have the a.out header, we can read it. And of course, by just reading the header, we can recognize the sections of the object. And a standard Unix binary or standalone binary, VAX style, VAX style, has several sections. Code, which is text, as well as BSS, as well as data, as well as stack. So, the VAX way, something like 30 years old, probably more like 40 years old anyway, we are still using something like this just to be capable of loading the very loader. Well, is the present. And actually, it's quite smart to use the VAX way, the a.out way, because it possesses very simple header with very few entries in there, so you can load it immediately. So, we have a.out header. Read it. Of course, we have to read it into memory. We are in real mode, so we only have a few hundred kilobytes anyway. And of course, then we have to know where the object is contained, what are the actual sections of this object, and load them. But we will have to relocate them because we don't have much memory. We only have 640 kilobytes. So, what we will do next? There is one option, loose protected mode, which is entering protected mode just to access some memory. And the wisest approach is BIOS in 15H, hexadecimal. It provides us with several different functions which allows us to enter protected mode or just copy some buffers from real mode address space to protected mode. We will have to provide it with the segment descriptors. Anyway, for those of you who know what x86 protected mode is, you understand quite well. Or we can be idiots. Of course, we can always be idiots. And use the very rustic way. Load global descriptor table, load interrupt descriptor table, load machine status word, store machine status word, which is equivalent to move CR0 to register, move register to CR0, and of course we have to raise the protected mode flag. It's stupid because the very BIOS of ours provides us with enough functions, enough features to enter protected mode and copy from our real mode code to somewhere else, to the protected mode space, to the full space. Or there is another approach. Have you ever heard of a real mode? It's something which is not exactly known around here, I suppose. A real mode is just like real mode with a difference. Your data segments are capable of addressing 32 bits of memory, which is 4 gigabytes every time. It's done in a very simple way. You have to enter protected mode and load your segment registers with 32-bit selectors, segment selectors. And the very moment you leave protected mode, it's going to stay like this. The processors are copying their things inside some very, very internal structures. So, if you enter unreal mode, you end up with access to 4 gigabytes of memory, 32 bits only. So we can also use this mode to copy our loader into memory. And of course, the Unreal mode is quite similar to the system management mode, which is real mode, 16 bits way of working of the system. It deals with some BIOS functions. It's being executed on every single PC hundreds of times per second, every time. The procedures written in there are part of the system BIOS. Even though you're running high-end operating systems like Linux or Windows or Solaris or FreeBSD or whatever BSD, etc., your CPU, your CPU is still using some cycles to run its own, let's say the motherboard sequences. The SMM code is always pretty much linked to the motherboard. You cannot use another SMM sequence on another motherboard. So the Unreal mode is pretty much like system management mode. Now, something which is legacy from the file system checking IBM, FSCK Inc. IBM. Gate, few of you might have gotten the punch. Anyway, Gate A20. A20 is a very special thing because the 8086 CPU can address more than 1 megabyte of memory. How? The way it addresses it is the old school segmented way, which means that if your segment register is loaded with something high, you'll be able to access about let's say a few dozens of kilobytes on the top of your address space, above the very megabyte limit. So, to be compatible, IBM decided to set a very special limit, which is called gate A20. So, you won't be able to access the memory above 1 megabyte, and every single memory page anywhere which has A20 raised. How it's done? Very easy. You have to reprogram your keyboard controller. Long time ago, they did not have a lot of hardware in there on the main board, so they decided that they can use the keyboard hardware just to enable the gate A20. If you don't enable it, your protected mode will never work properly, because every address with A20 set to 1 won't be there. It's going to revert back to null, to 0, which is bad. So you have to enable it, and once you enable it, you'll be able to enter protected mode, the proper protected mode. So, by just reading parts of /boot/loader and relocating its pages somewhere in your memory, you'll be ready to kill MS-DOS. And how would you do this? Very easy. You have to issue clear interrupts, which means that all of the interrupts are not reaching the processor, excluding the non-maskable interrupt, which is already quite bad anyway. And then you have to long jump to the BTX entry point. And it's pretty much enough. Once the BTX microkernel is up and running, the rest of the system is going to boot by itself. So the very loader, your MS-DOS loader, will have to deal with /boot/loader. It will have to load it and then start it. And of course, the entry point is in the A-out header. It's of course prefixing the very loader image. You can always use it, and we said that we are going to load it anyway. So we know the linear address of the long jump. It's extremely well resolvable. The rest, well, the loader is going to do the rest for us. It's really nice of it. I would have said him, but it's not alive. So, the next thing, you have, I know. You have to have your proper memory disk in place, your memory disk image in place, because if it does not happen, your Berkeley Unix kernel is going to boot and is going to find exactly nothing as a root file system, which means that you end up in panic. So you must provide a proper memory disk image. It's not so hard to make one. So proceed. You can use these slides and the software I have on my website just to do this, it's going to panic anyway. So, the code, bootloader plus MS-DOS. The source is at this address. There is a crafted QR code here, which points to the exactly same address. I have written the same code in two different languages, Borland C++, C++ 3.1, and of course Borland Pascal 7. It works. And the license is Berkeley license, the 4-clause one. I'm sorry, I don't like the 3-clause one. Use it. If you don't remember, Alt F9 or Control F9 is the very sequence you have to issue from your IDE. Everybody rise. This talk is dedicated to Dennis McAllister Ritchie and John McCarthy. The first one is creator of Unix and the C programming language. The second is well known for creating Lisp. They both died last month. So I suppose it's not so bad to just recognize what they did to society. We wouldn't have had Unix or anything Unix-like. But they're not here anymore. And I suppose it's right to recognize their memory. And that would be their programming. Dennis returned 0. And McCarthy went through this function, which returned nil. It's Lisp. I don't expect you to know it anyway. Thank you. Thank you for attending my talk. Someone else also died last month. No, it's not funny. It's clever, but certainly not funny. I said it's not funny. There you go. Anyway. Тъй. Ами, свършихме. Това искам да остане до следващата лекция. Денис McAllister Ritchie. Request-cut impake. Джон Макарти, request-cut impake. Разкачи ми всичките свищини, които имам по себе си. До той това и това не знам